this FOG is continuous at x0 equal to this for any neighborhood of this point FOG of x0. Okay, this inverse image must be a neighborhood of x0. So we must assume M is a neighborhood. Let me, this is M for example. Okay, if M is a neighborhood of this point or this point, since F is continuous at this point, the inverse image of this under F must be a neighborhood of G of x0. Then since G is continuous at x0, the inverse image of this set under G must be a neighborhood of x0, but this is equal to this. And so we have this property, and FOG is continuous at x0. Please note that we can see the proof of this equality easily. X belonging to this set, this is an inverse image, okay, equal to FOG of x belonging to M. You know this definition, the definition of inverse image. FOG of x belonging to M, and this is equal to this condition, F of G of x belonging to M. If we consider this as an element such as y, F of y belonging to M equal to y belonging to the inverse image of M. Y belonging to inverse image of M, but we consider y equal to G of x, so that G of x is an element of this set, so that x must be belong to the inverse image of M, so that these two sets are equal. Wa alaikum assalam. Welcome, Abdul Rahman. So that we have this proposition, the composition of two continuous function is continuous. Okay, let me see. Okay, now let's me express the definition of a tour. A relation such as this on a set X is an ordering when the following three requirements are satisfied. We refer to such sets as ordered sets. These three conditions. For any alpha in X, we have this relation. If alpha have this relation by if we have these two conditions, then alpha equal to beta. So if this relation have this three property, we say that this is an ordered set. And an ordered set is called directed when for any alpha and beta in X there exists another element such as gamma, such that we have these two properties. Okay, two properties. Ordered set are very, very important, and we can generalize the notion of sequence in topological space by this object. Okay, for an easy example, we know that real numbers with ordinary order in R, A is less than or equal B if and only if B minus AB non-negative, is an ordered set. This relation on real numbers have these three properties. Any alpha in real numbers have this property: A is less than or equal A. If A be less than or equal, if alpha is less than or equal beta and beta is less than or equal gamma, then alpha is less than or equal gamma. If A be less than or equal beta and beta be less than or equal alpha, then alpha must be equal to beta. We have these three properties in ordinary order in real numbers. Okay, and also you know that a relation on X is a subset of X times X. You may consider, for example, S, for example. Okay, or by the notation of our book, you may consider this relation as a relation on X. Okay, sorry, I have dear students, do you have my voice? Thank you, Muhammad and Sajjad. Okay. Okay. So if this relation have these three properties, this relation is reflexivity. We say that this relation is reflexive, and this relation is transitivity. This relation is transitive, and this relation is antisymmetric. We say that this relation is antisymmetric. Okay. 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 Okay, I mentioned that note that if x is a set, then a relation on x is a subset of x times x, such as R or this relation, for example. So that if we consider a relation times x, or this relation has a subset of x times x. So that, please note that this is a notation, okay? This or R are subsets of this product space or product set. Now this three property can be rewrite by this. For any alpha in x, we must have this must be belong to R, because in relation you know that. Let me write this at first for you. By this notation, x and y is an element of y if and only if we have this relation. Or by this notation, x and y is an element of this relation if and only if we have this, so that this is another notation for this. So we can write this definition ordered set whenever we have this property. X and R, for example, is an ordered set sorry. Okay. X and this relation is an ordered set, okay? If and only if we have these three properties: 1, 2, and 3. For any alpha in X, we have this property: alpha and alpha belong to R. 2, for any alpha, beta, and gamma in X, if alpha and beta belong to R and beta and gamma belong to R, then alpha and gamma belong to R. And 3, for any alpha and beta in X, if we have alpha and beta is an element of R and beta and alpha is an element of R, then alpha must be equal to beta. These three conditions equal to these three conditions. Okay, properties that you can this x is called directed if and only if we have this property for any alpha and beta in x. There exists gamma in x such that we have these two properties, alpha and gamma belong to R, and beta and gamma belong to R. So that you can replace this condition by this condition. Okay. Okay. And finally we have the definition of a net. A net such as this is a set in a set X. A net in X is a function from a directed set such as A to X. Any function from a directed set to X is called a net on X. A net is generalization of a sequence. We can take subnets of a net in exactly the same way we take subsequence of a given sequence. Okay, let me see this. I have some problem by this board. Okay. Now, by the definition of a net, we can define convergence in a topological space. Let X and tau be a topological space. We say that a net such as this in X converges to X when for all neighborhood of X there is an index such as alpha n in our directed set, such that for any alpha with this property X alpha belong to n. This is very similar to the convergence of sequence. Okay, this is denoted by this, or the limit of X alpha equal to X. Okay, Okay. Let me write again. Let me read this again for you. Let X and 2 be a topological space. We say that a net such as this converge to X when for any neighborhood of X, neighborhood of this limit point, there is an index such as alpha n, such that for any alpha with this property xn belong to n. Okay, xn belong to n. Okay. Dear students, do you have any questions? Okay. So that xn, for example, or x alpha, okay, or by this notation we can write the limit of x alpha equal to x. This equal to this condition for any neighborhood of x. There exists an alpha n please note, assume that this is our, for example, net. Okay, such that for any alpha with this property, alpha with this property, x alpha belong to or n or this neighborhood. Okay, this belong to n. This is a generalization of the limit of sequence, because if we say that For example, in a topological space, the limit of xn equal be a metric space. Okay, xn is a sequence in x, and x is an element in x. This equal to for any epsilon there exists an natural number. Let me write this by another notation, such as m, okay, such that for any n greater or equal n, we have d of xn and x is less than epsilon. But it is important that this is equal to this equal to xn belong to the ball by the center x and radius epsilon. Okay, so that this epsilon leads to a neighborhood. So for any n equal to an epsilon, there exists a natural number such that if n greater or equal n, then xn belong to or n, and we see that this definition exactly a generalization of the limit of sequence in metric spaces. Please note that we consider this as an metric space, okay, as an metric space. This is a metric space, okay. Okay, let x be a metric space. Then we have this as the definition of limit in for sequence. So it's very important that this definition is a generalization of limit in sequence. And we have this proposition: let X and 2 be a topological space and S a subset of X. The closure of S is the set of all points in X such that are a limit of a net in S. This can be worded as X is an element of S bar if and only if X is the limit of a net in S. And this is very, very important. In any topological space, okay? If we consider any, for example, S as a subset of X, X is a topological space, not a metric space. Topological space are a generalization of metric spaces, okay? We have this property: X is a point in S bar, the closure of S, if and only if there exists a net such as this, a net such as this, in S such that X equal to the limit of this X alpha. X belong to S bar if and only if there exists a net in S such that X the limit of this net. Okay. And the proof of this is very similar to this proposition to metric spaces. That we can see the proof of this. Consider Mx as a directed set. The set of all neighborhoods of X is a directed set by the inverse of inclusion. It is not that M have this relation with N if and only if N is a subset of M, not N. We say this relation as opposite direction, opposite inclusion, okay? For any M and N in N of X, for any two neighborhoods of X. Okay? Now assume that X belongs to S bar. By definition, 2.10. We have that for all neighborhood of X, there exists an element in this intersection. This intersection must be non-empty so that we have an element in this set. We see that this net Xn such that N belong to Nx. Please note that for any N in Nx we have an element in this intersection, so that we found a net by this directed set, and this net converges to x. This is because all neighborhood of x contain x. For the other direction, that this net be a net in S such that converge to x. Assumed by way of contradiction that x not belong to S bar. So x must be belong to the complement of S bar. We call that S bar is closed. This implies that this competition is open. Since S bar is closed, the complement of S bar must be open, which means that this is the neighborhood of x, because x belongs to this and this is an open set, so that this is a neighborhood of x. But we assume that this net converges to x and converges to a point outside of S bar. So there exists some alpha n such that for any alpha greater or equal alpha n, x alpha belongs to this open set, and we know that this x must be capital X, not S bar. Okay, we know that. We know that S is a subset of S bar, so that the complement of S bar is a subset of the complement of S. Okay, the complement of S bar is a subset of the complement of S. So since x alpha belongs to this set, must belong to this set x minus S for any alpha greater or equal alpha n. This is a contradiction, since this is a net in S. All of x alpha must belong to S. But we prove that these elements not belong to S, and this is a contradiction. Okay, so that we have this very nice proposition that I write this in this line: x belong to S bar if and only if there exists a net in S with this property. Okay. Okay. And we have this corollary: a subset of X is closed if and only if every net in F that converges in X has a limit in F. Let me show this for you. Okay. This is our corollary. F is closed if and only if F bar equal to. We know this for any subset in topological space. Okay. F is closed if and only if the closure of F equal to F. And this is equal to this condition. F bar is a subset of F. Because F always is a subset of F bar. And this is equal to this condition. If X belongs to F bar, then X belongs to F. But X belongs to F bar equal to this by the previous proposition. X bar belongs to F bar equal to, there exists a net in F such that X alpha conveys to X. So that we can write instead of this closure. Now this must implies X belong to F. Okay? And this is very nice corollary. F is closed if and only if every net in X that converge has a limit in F. Has a limit in F. If we have a net in F that converges to X, this X must be belong to F. Okay? Must be belong to F. And we have this proposition: a topological space is Hausdorff if and only if every convergence net in the space has a unique limit. And we don't have the proof of this for you. Okay, this is very nice proposition. And its proof is easy because for example, let's X and 2 be Hausdorff. Okay. And X alpha be a net in X such that X alpha tend to X, X alpha tend to Y, and X non-equal Y. So we have three conditions, okay? 1, 2, and 3. From 3 we have, because X is household, okay? X is household. There exist two open sets such that X belong to U, Y belong to V, and the intersection of U and V equal to empty set. From this and 1, we see that there exists, for example, alpha U in order set such that for any alpha with this property, X alpha belong to U. And from this, by this condition, there exists alpha B, for example, such that for any alpha with this property, X alpha belong to V. But this is a directed set. So if gamma be greater than alpha U and greater than alpha V, we have these two properties. X alpha must be belong to U and must be belong to V. This is a contradiction because these two sets must be disjoint. This is a contradiction. So that if X non-equal to Y, we have contradiction. If X alpha converge to X and also converge to Y, X must be equal to Y. Okay, dear students, do you have any questions? Do you have any questions? Oh, goodbye.